A very good morning to all. Welcome you all in the ISFCP dialogue series under the aegis of IQAC-IIC ISFCP, organized by ISF College of Pharmacy and Autonomous College, Moga, Punjab. We welcome you all in this online dialogue series. Today's guest and speaker, Mr. Gurpreet Singh, Assistant Professor in Department of Pharmaceutical Chemistry. We welcome you, sir, and requested to please proceed further. Sir, please.
Thank you, sir, for inviting me to this ISFCP dialogue series, which is conducted under the aegis of IQAC, IIC, ISFCP. So, today's my topic for the presentation is Retrosynthesis Analysis, Unlocking the Secrets of Organic Synthesis. In this presentation, we are going to discuss about the retrosynthetic analysis and how it is helpful in the conducting organic synthesis and building the molecules in a simple manner. I, Gurpreet Singh, working as assistant professor at the Department of Pharmacy of ISF College of Pharmacy, welcome you all to this dialogue series. Let's start with the presentation. These are the contents of my slide: introduction, a brief about the retrosynthesis and its importance in organic chemistry. Then we are going to go perform the retrosynthesis analysis with its definition and very few examples which have been selected from the textbooks as well from the internet resources. Then we will discuss about how to choose a disconnection. Then at the end of the presentation, I will give which are available on internet for performing the retrosynthesis analysis. And finally, I will give you some advantages or applications. So first, introduction. So let's start with the introduction of organic synthesis. Organic synthesis, as you know, it's a branch which is related to the chemistry or generally focused on the construction of the molecules through very complex chemical reactions. As you know, organic reactions or to create some complex molecule, there are different steps or which are needed to be executed by very sophisticated procedures or which are needed to be designed to create that desired molecules. So organic chemistry, it is vitally applicable in drug discovery, material science, and the production of very fine chemicals. So there are some challenges which a chemist might face synthesis. First, the complexity of the target molecule. We must know about the complexity, how much your molecule is complex. Is it very easy to synthesize or it is having very complexity like radioselectivity and chemo selectivity, and moreover, I say it is open chain or it is a branch chain or it is a close or a spiro compound. We must know about these things. Then the synthetic feasibility, whether it is easy to synthesize, it took how many steps it will take, or these steps are easy to control, what should be their selectivity and control over the reactions. Next, fourth is the reaction optimization. This reaction optimization is very much needed process for carrying out successful organic synthesis. In these things, the reactions steps are optimized for the different conditions like temperature, pressure, amount of the starting material required, and the other things. And most of the time and resource constraint is there. Time, how much time it will take. Some reactions take only 5 to 10 minutes to happen. It might take 24 hours. It might take a days, number of days. That will halt the progress. So we must look at these time frames and the resource constraint, how much resources you have. Like if you are performing the total synthesis, whether you have the final molecule in your hand or not, its structure is validated or not. And for performing that synthesis, you need what kind of chemical you need. Is it easily available? It is, or it must be synthesized during the process. Or the other thing is what is the cost of that resource? Like some chemicals, you might get 500 rupees for a few grams, and for other chemicals like very sophisticated catalysis, you need to pay lakhs of rupees for just 1 gram of the chemical. So these are the constraints And to overcome these constraints, we have a tool that is known as retrosynthetic and synthetic analysis. Retrosynthesis, or you can call it retrosynthetic analysis, it's a very powerful tool in organic chemistry which help you to plan very complex organic synthesis in a simple manner. What we do in this, we have a target molecule, we identify the sequence of the simple precursors which actually correspond to the original molecules. So the basic goal of this synthesis is to simplify your synthetic plan by breaking the target or complex target molecule into simple starting materials, which are easily available or which can be easily produced in our labs. So that will allow to overcome the earlier discussed the problems. So just for example, here we have this Z molecule, which can be synthesized from X or Y. So we need to design a scheme using the retrosynthesis from X or Y chemical to synthesize the Z target molecule. So here I am just showing the first two examples. Like we have examples of benzyl benzoate. It's an ester, and as you know, esters are made up by the reactions of alcohol and acids or acid chlorides. So if we perform the retrosynthesis, we came up with the two compounds, one phenylmethanol and second is benzoyl chloride. And if they are reacted in the presence of some base, the ultimate product is benzyl benzoate. And another example is the drug amlodipine. It is an antiarrhythmic drug, which is if we disconnect this molecule from this here, we will end up with 4-nitrobenzoyl chloride and 2,6-dimethyl-aniline. So in this reaction, this amide linkage, CONH, should be made. So for that, we need two feasible chemicals. Like here we have benzoyl chloride, nitrobenzoyl chloride, and here we have dimethyl-aniline. And from these two, when they react with one another, with the loss of hydrogen chloride, it will give you the drug which is needed. So we are performing, first we are assuming what should be our target molecule, and then we are disconnecting the target molecule into simple feasible chemicals to synthesize it in a simpler manner. That is the actual value of the retrosynthesis analysis. So there are some important definitions which might be needed for the time. First, the target molecule. It is the molecule of our interest. Then retrosynthesis analysis. It is the process of imaginary breakdown of molecule into progressively simple starting material. The reaction are viewed in the retrosynthetic direction, or it is viewed in the reverse direction of the synthetic process. Disconnections. These are the imaginary cleavages which correspond to the reverse of forward reaction leading to immediate precursors. Or they are also known as transformations and indicated by the wavy lines as shown. You can see we have nitrobenzene. If we disconnect the CN bond, we will end up with the benzene and nitrate group. Then we have retrosynthetic arrow. It is the arrow used to show the retrosynthesis. It is just a simple arrow with a one-headed head and two parallel lines. Next are the synthons. Synthons are the imaginary fragments that are obtained by the disconnection, and they must be present into our final compound. Like when we perform the retrobenzene by breaking the CN bond, we end up with these two fragments, which are our synthons. And performing the retrosynthesis of cyclohexene into 1,3-butadiene-eth. These are our two synthons, and if you join these two, they will end up with the cyclohexene. Then next are the retrons. Retrons, each reaction generates a characteristic structural elements differentiations, the substructures, they are called as electrons, and they must be present within the target molecule to be which must be applied to corresponding transformation. So we have this target molecule, and these are the basic precursor, and this is its synthon or retron part, which must be present in our molecule. When you join these two with the loss of water, it will join here and form this molecule. Next are the reagents which we need to use to perform the synthesis. Like one need to go for this nitro group generation. The simplest thing is you just react the nitric acid, concentrated nitric acid with concentrated sulfuric acid under controlled condition. That will lead to generation of nitrate group. And if you need bromide ion, you will go for the bromine. Next is the retrosynthetic tree. What is retrosynthetic tree? Retrosynthetic tree is a complex pattern of retrosynthesis analysis which might lead to different possibilities which one has identified to synthesize a single target molecule. So there are more, there is the retrosynthesis gives you more number of possibilities, different possibilities to synthesize one molecule in a different pathways by applying different starting materials or different routes. Like we generally observe in these in the research papers, like one person has synthesized one molecule by one pathway, another one is using the second pathway. So there are number of pathways you can use. So it will another you can see the each substructure. If one or more disconnections are required, you can go for the different pathways, and you can change the target molecule. Even the intermediate can be retrosynthesized if the intermediate is not available for the commercial values. So it will generate a second pathway. And if those intermediates are needed to be synthesized using retrosynthesis, it will generate more and more pathways. Like we have this graph, what is showing, we have a target molecule and we have simpler A1, A2, A3, A4, and A5 pathways. So this is the basic retrosynthesis. There are 5 pathways have been generated, and from those 5 pathways, you can see that there are nearly 20 pathways which have been separately generated. You can go for let A3 has been synthesized by can be synthesized by 4 processes, A4 again 4, A5 3, A2 with 5, and A1 is with 4 processes. So there are some further simplification. What is the more main purpose of this retrosynthetic tree is to simplify your target molecule. You can perform more than one retrosynthesis. And that retrosynthetic pathway leads to more of your molecule and help you to design your synthesis in a more efficient and effective manner. You can find the different pathways. So that according to you can choose what you need from those pathways. Like some pathway might fail during the actual process, or some pathway do not have proper disconnection. So choosing the disconnection is very much important, or it is the hardest part of designing a retrosynthetic pathway, or spotting the disconnection is very much hard, or it is a very much important process during the retrosynthesis analysis, choosing the disconnection. For this, there are some guidelines which we discuss with every examples in the next slides. So first, the guideline 1, what it say, disconnection must correspond to known or reliable reactions. Like you are disconnecting the molecule, and if you are ending some non-realistic reactions or non-reliable reactions which never end up, or which the intermediates you have formed that are non-reliable or not stabilized during the reaction, you have not end up with your final product. That might lead to some kind other reactions or no reaction. Like you can see in this we have break down this CO ether linkage, and we have ended up with dichlorophenoxide ion and this acid ion. Then how you will make them? How will they end up with the final product? So this is a bad connection. So first point says your disconnection must be good and it must be reliable and must lead to a simpler chemical reaction with the available reagents or the reagents which are commercially available. So this is the guideline. So in this, both this oxygen, it cannot directly attack this, and this group does not directly attacked by this because both groups get inactivated during the course of the reaction, and there is no such reaction, and this is totally an unreliable reaction. Next, guideline 2. Guideline 2 says for a compound consisting two parts joined by a heteroatom, disconnect next to the heteroatom. Guideline 2 says that when there is a heteroatom in a disconnection, or the two parts of an atom which are joined by a heteroatom like nitrogen, oxygen, or sulfur, the disconnection must be made at the next. Like in this molecule, chlorbenicide, we have break that sulfide molecule. And for this, we have easily available starting materials like 4-chlorobenzene thiol, which is in the presence of base, and 1-chloro-4-chloromethyl benzene, which again in the presence of base generate this molecule. And if we react these two molecules in the presence of sodium ethoxide and ethyl alcohol, we end up with our final product. So always try to break the molecule which is joined by heteroatom next to the heteroatom so that a feasible synthesis can be performed. So there are some other examples, like we have cetabin ethyl ester. For the retrosynthesis, there are two retrosyntheses. You can see I have already talked if one retrosynthesis is not feasible, you can perform the second one. So in this, first we have this total ester. We have break first amide bond, this amine bond into RPR and this ester, amino benzoate ester. Then we have performed the retrosynthesis because esters are generally not available in market as such. So for the retrosynthetic analysis, we have gone, as we know, the esters are made up of alcohol and acids. So we perform the retrosynthesis analysis next to the heteroatom by breaking this bond, and we end up with 4-amino benzoic acid and ethyl alcohol. And for synthetic route to need to be developed, first 4-amino benzoic acid needed to be esterified using ethanol and acid to this benzoate ester, and then the final group must be added to this by using the appropriate reagent, and we end up with cetabin ethyl ester. So in this retrosynthetic analysis, we have performed two syntheses, or you can say we have performed two retrosynthetic analysis. First, we break down the original molecule into two parts. Then we break down the obtained ester part into two feasible methods, and then we perform the actual synthesis. Next, guideline 3 says, consider alternative disconnections and choose route that avoid the chemoselectivity problems. Like there must be more than one possible disconnection in a single molecule. So we have to identify those routes which are devoid of problem of chemoselectivity. So if we perform the retrosynthetic analysis of ICD D7114, you can see there are four possible routes, like A route, B route, C route, and D route. And if you look at A, B, C, D, so there is a generation of cation which is not easy to synthesize or which is not stable during the reaction. But if you follow the C pathway, you can see there is formation of two full molecules like phenylbenzene, phenylmethane, phenylmethanamine, and one benzoyloxy, 4 bromomethoxy benzene. So we go with the C pathway. So if we go with the C pathway, we end up with this molecule, which again, this is easily available. Phenylmethanamine is very easily available, but this molecule we need to synthesize. So we again perform the retrosynthetic analysis. So in this, what we need, we again have two choices. We are applying the guideline 2 next to the heteroatom. So we go with the two processes. Like we are breaking the molecule next to the heteroatom, this oxygen and this oxygen. So here there are two pathways again, E pathway, we are ending up with a non-feasible cation form. And then we are also ending up with this. Then again in the F pathway, we are going to end up with this molecule and this dibromoethane. And finally, if we again break this, we end up with this dihydroxybenzene and this phenyl chloride. Then if we actually need to synthesize, what do we need to do? First, we hydroquinone, and then we treat it with benzyl chloride to form this intermediate. We are going to form this intermediate first. So for this, we choose hydroxyquinone and benzyl chloride, and it will get up our required intermediate. Then we treat this intermediate with the base, in the presence of base, with the dibromomethane to end up with this intermediate. Finally, we treat it with benzyl amine, and then it will give you your target molecule. So in this, we have different pathway, but we need to select toward that pathway which is devoid of any chemo selectivity problems. Next is the functional group interconversions. Like some functional group are easily accessible or easily can be made, but some functional groups are not easy to make. Like if we are going to synthesize aniline, the simplest reaction is to convert the nitrobenzene to aniline. Nitrobenzene, has disconnections of benzene plus nitrate group. First, you need to synthesize the nitrate group, then you reduce that nitrate group to the amine. So that is the functional group interconversions. Like if the group cannot be directly synthesized or directly attached to the molecule, then you need this approach. You can convert one functional group to the another functional group. Like I given you two examples. First is the synthesis of aniline. If you go for this, your first functional group interconversions, the retrosynthesis, we have nitrobenzene, and if you perform CN disconnection, we end up with these two syntheses. First, we need benzene, which need to be nitrated at the appropriate position using the appropriate reagent to synthesize nitrobenzene. Like for nitration, you can use this sulfuric acid and nitric acid. And then you synthesize aniline from this nitrobenzene by reducing this nitrate group to the aniline using tin HCl or zinc HCl, these which are very commonly available. And another example is the synthesis of 4-bromoaniline. As you know, aniline, this group, how to synthesize? First, you need aniline, which is we have already synthesized. First, you need to protect this group by acetylating it. Otherwise, during the reaction, bromine might attach here, or might be there is formation of some other kind of intermediate which is not required. So first, what we are doing, we are protecting this group with the acetate group to convert into the benzacetamide, and then we are performing the bromination using bromine in acetic acid, that it will lead to 4-bromoacetamide. And then finally, we are going to perform the hydrolysis. But through hydrolysis, we are removing this acetate group and to reach to our final compound, that is 4-bromoaniline. Next, guideline 4. Guideline 4 says 2 group disconnections are better than 1. If there is single group disconnection, that might lead to irrational reactions, or you can see we have already seen some examples. And then you can use the two group disconnection. These are divided into two parts: logical and illogical synthesis. Logical or rational synthesis, where we have some rational, like you are going to synthesize 1,3 bifunctional and 1,5 bifunctional compounds. Irrational, where we don't use any logic, it just disconnect it and synthesize, like for 1,2, 1,4 by 6 bifunctional compounds. So we're going to having some examples. The first, logical connections of 1,3 dioxygenated skeletons. First, for this I select beta hydroxy carbonyl compounds. For this I am using the retrosynthesis of 2-ethyl 3-hydroxyhexane. If we retrosynthesize it, it will end up into butyraldehyde and its enolate form. This is the enolate cation. And then the final compound, what we need to synthesize is the butyraldehyde. So the final reaction, how to synthesize this target molecule. First, you need 2 moles of butyraldehyde, treated it with base, and then there is an in situ generation of this enolate ion, and another molecule attack this enolate ion and to form this 2-ethyl 3-hydroxyethanol hexanal compound. Then we have some example of 1,2-dioxynitric compound alpha beta unsaturated carbonyls. Like for this, I am using the example of 3,4-nitrophenyl acrylaldehyde. When we retrosynthesize it, we end up into two pathways: 2-hydroxy 3,4-nitropropanol or 3-hydroxy 3,4-nitropropane. So just they are isomeric, only the difference in the position of this. But this is very hard to make. This is easily available. So we go with this. And to form this compound, we have 4-nitrobenzaldehyde with acetaldehyde. So first, what we need to do, we need 4-nitrobenzaldehyde that should be treated with excess of acetaldehyde in the presence of KOH and alcohol to form this final compound. Then 1,5-dicarbonyl compounds. For this, I'm using the retrosynthesis analysis of nonane 3,7-dione. For this, what we need, pentene 1,3-dione and butane 2-one. Or you can either go for this both pathways, pentene 1,3-1-ene 3-one or butane 2-one. For this, you can go for either way. You're just reacting either of these reagents in the presence of a base, and you are ending up nonane 3,7-dione. Next, we have some illogical connections where we don't apply any reasoning or logical approach to connect the molecule. In this 2-hydroxy 2-phenyl propionic acid, what we need, acetophenol and acid ion. How to generate this acid ion? By acetic acid. So if we use like acid ion is generated. So 4 common reagents. For what is the common synthone for acids? It is the cyanide ion. So we need cyanide ion first. For the synthesis of that molecule, we start with acetophenol. We treat it with hydrogen cyanide and we end up with this functionality. And then we hydrolyze this functionality to get our desired compound. Fine, then we have some 1,2-diketodiols like retrosynthesis of 2,3-dimethylbutane 2,3-diol. When these such kind of functionalities are present, we need functional group interconversions. In that, these two functionalities are converted into carbon-carbon double bond. After that, you can apply the Wittig reaction to get the desired compound. First, we have done the retrosynthetic analysis. Look, like we start with the acetone and we are performing the Wittig reaction, which is performed in the in the presence of phosphorus halides that will leads up into this intermediate compound. And this intermediate can be this C carbon-carbon double bond. It can be easily oxidized with the help of osmium tetroxide that will lead to hydroxylation or to the desired compound. However, the osmium tetroxide is very drastic to use. That require very specific condition to be used. Next, we have some 1,6-bicarbonyl compounds. So First, for this, I use the example of 6-oxo, 6-phenyl hexanoic acid. So during the retrosynthesis, first we need to perform the retrosynthesis of this molecule. We end up with 1-cyclohexenyl benzene. Then we use the functional group conversion to convert that 1-phenyl cyclohexenyl 1-ol, and then we perform the retrosynthesis with, we end up with a cyclohexanone and phenyl magnesium bromide or the Grignard reagent. And the final synthesis, we start with the Grignard reagent, phenyl magnesium bromide, in the presence of magnesium and ethylene oxide and cyclohexanone. We end up with 1-phenyl cyclohexene 1-ol. Then we use the phosphoric acid, and we end up with the 1,3-cyclohexenyl benzene. And then we ozonolize this molecule. This will lead to open up this side chain from here, and we end up with 6-oxo 6-phenyl hexanoic acid. Then there are some reactions which can be used, which can be performed by a Diels-Alder reaction. Like for this, I use the example of butane 1,2,3 tetracarboxylic acid. So in there we use some reconnects, or you can say retrosynthetic analysis. We end up with the cyclohex 4e 1,2-dicarboxylic acid. Then you just perform the Diels-Alder reaction or retro-Diels-Alder to break the molecule into 1,3-butadiene and malic acid. So if we start with the synthesis, what we need? Butadiene, furan 2,4-5-dione, that will lead to the molecule that isobenzofuran 1,3-dione. Then we oxidize it, ozonolize करेंगे हम इसको, and we ozonolize it in the presence of hydrogen peroxide to end up with this dicarboxylic reagent. And in the presence of base or followed hydrolysis, it will end up with the butane 1,2,3,4 tetracarboxylic acid. So there are, this is the almost last slide, the retrosynthesis of heterocycles containing 2 nitrogen. For this, I take the example of 3-methyl 1H pyrazole 5,4-on. We first disconnect the CN bond to reduce it to diamine and ethyl 3-oxobutanate. So for the synthesis of target molecule, you just need to react these two in the appropriate conditions to achieve the final synthesis. So there are some helpful tools, or you can say internet resources, which are available free or paid versions, by which you can perform your retrosynthesis analysis in a simpler manner, like Rexis by the Elsevier group, Cynthia, it is owned by Merck, SciFinder by American Chemical Society, and IC Synth, it is freely available, which is developed by the University of California. These are the, let's take out the advantages or application. First, it will help you to plan your synthesis in a statistical manner. So you know what kind of reagents you are kind of conditions you are going to do. So it will reduce the extra burden of chemicals as well as time. Then it will simplify the complex structure. Like we have very complex structures of natural molecules. It will help you to reduce them into simpler molecules. Access to diverse starting materials. You can use diverse range of starting material available commercially, which you can use in your synthesis. You have a streamlined synthesis. This synthesis is very easy. You know what kind of problem you are facing. You can easily overcome that. It's a very good problem solving tool. And it's more, it is versatile and give you better creativity. And finally, it can use for education and training of the students. And finally, it is apply to total sense of your natural products. These are some references. Thank you. If you have any questions, you can ask.
Thank you, Dr. Gurpreet Singh, for this kind information regarding the significance of retrosynthesis. So you can please stop your presenting. Yes. So we are very thankful to Mr. Gurpreet Singh for his excellent lecture on retrosynthesis and its significance in pharmaceutical sciences. And all the listeners, if you have any query, please drop your message in our YouTube inbox, and please or visit our website www.isfcp.org. Thank you, Mr. Gurpreet. Thank you so much.
Thank you, sir.